Okay, good morning, everyone. Today we'll cover the rest of the theory for chapter 3, which is inductors and then capacitors. The homework for this chapter is due on Thursday. Do not wait to get started on the homework because a lot of those questions are conceptual questions. You will be able to answer those based on the previous lecture as well as today's class. And then Wednesday, I will cover the problems. And so you'll be able to do the rest of the homework after Wednesday. And again, today is Monday. Do not wait to get started on that homework, right? You'll be able to answer most of the questions, the conceptual questions based on the previous lecture as well as today's lecture, right? So let's look at the class notebook. In section 4, stopped here, and here's the primary equation. Okay, so inductors and capacitors, they are very similar to each other. They are duals of each other, and the equations that you will see for the inductor and the capacitor are very similar in structure. First up is the VI equation, meaning determining the inductor voltage when you are given the inductor current. For the inductors, we'll primarily use current as the input quantity. For a capacitor, we will primarily use the voltage as the input quantity. Okay, but we have the VI equation, then we have the IV equation, basically how to find the current if we are given the voltage for both the inductors and the capacitors. So voltage for an inductor is given by the equation L di over dt. Product of the inductor, L, is the derivative of the current as a function of time, rate of flow of current, di over dt. They are both energy storage devices. Energy is not transferred in an instant, so the voltages and currents are both dependent on time, hence function of time. So notations would sometimes just be V. It could also be V of t, V or V of t. Similarly, current could be current I or just I of t. Sometimes we use a subscript to refer to the specific component. So we might also see VL or VL of t, okay, or IL of t. In all cases, they are referring to the exact same thing. It's voltage and current, and that's it. Depending on the circuit, depending on the author, depending on the quantity we are trying to solve, it may or may not be given as a function of time. But as an engineer, it is up to you to understand and realize that it could be anything, right? Voltage and current for an inductor and a capacitor is always going to be a function of time. Okay, so if it may be given as I of t or V of t, it may not be given as I of t or V of t, but they all mean the exact same thing. Okay. So voltage V is L di over dt. If you wish to find the current, simply integrate both sides and you obtain the equation that is shown below. I of t is 1 over L integral of the voltage. Okay, and we will look at this a little bit more closely when we get to the example problems. Okay, but simply it's a derivative when we want to find the voltage. It's the integral when we wish to find the current. For a capacitor, both the equations are flipped. The structure is exactly the same, but they are flipped. The limits of the integration is nothing but summation, right? Dx is individual slices, and then you add up all the slices between a certain period, right? And so in this case, T0 and T is simply when you begin your analysis, and the variable T is the end of your analysis. It's summation between a certain period. In this case, it's time. X-axis is time. So it's T0 is not the beginning of time. It's simply the moment in time where you begin your analysis. That's all it means. As an example, let's say you're monitoring a system for 24 hours. Okay. At the 59th minute, you want to analyze between the 59th and the 60th minute over that period of 24 hours. So in this case, T0, the moment you begin your analysis, is 59, the 59th minute. And the moment you end your analysis is the 60th minute. Between 59 and 60, hence T0 would be 59, T variable would be 60. Make sense? Right? So T0 and T could take on any value. And again, we will look at this in detail when we actually get to the example problem. But just so you know for now, T0 and T is simply begin and end of your analysis. Okay. Inductor voltage mathematically we expressed L di over dt. If I is constant, meaning the value of I does not change with respect to time, mathematically what happens? Di over dt goes to 0. Hence, the voltage goes to 0. Right? Easy to see that mathematically. Conceptually, this is what happens. Inductor is nothing but a conductor that is wound in a coil, right? That coil has a magnetic field. Energy is stored in that magnetic field. So when current first passes through the inductor, magnetic field arises, energy is being received and stored in that magnetic field. At a certain point in time, depending on the inductance level, it will reach the maximum capacity. When it reaches maximum capacity, we say that it has reached full charge. When the energy is being received into the inductor or the capacitor, we say it's being charged. When it flows out of these components, we say that it is being discharged. Once it reaches its maximum level, meaning the bucket is full, we say it has reached full charge. When it reaches full charge, the inductor behaves like a short circuit. Okay, current can pass through without any opposition. And again, as a reminder, the amount of time it takes to reach full charge, it depends on a lot of variables. Typically, it's very, very quick. Milliseconds, microseconds, right? It's not like days or weeks or months. It reaches that full charge very quickly because these components are very small in value. So again, current flows to the inductor, magnetic field is set up. Once it reaches full charge, it behaves like a short circuit. Current is passing through unimpeded. You have two ends of the inductor. If they are behaving like a short circuit, what is the voltage across those 2 points? 0. So mathematically, again, di over dt is 0. Conceptually, it's behaving like a short circuit. Steady state simply refers to the moment where it is fully charged or it reaches full charge. Okay, it reaches full charge. DC, whether it's DC voltage or DC current, has a constant value. So if you plot the value of a DC current or DC voltage with respect to time, time is on the x-axis, the value of the current does not change. If it's 5 volts, it stays at 5 volts. If you have a 1.5 volt battery, that battery will supply 1.5 volts irrespective of the time, right? It does not change with respect to time. So DC remains a flat line. So DC has a constant value, meaning when you apply DC current to an inductor, it starts charging, but once it reaches full charge, that value is constant, meaning it's steady. Hence, we refer to it as steady state. So at steady state, inductor behaves like a short circuit. Now let's take a pause, think on that. Let me know if you have questions. Yes. So that we will look at in chapter 4. So the question being asked was about the charging and discharging phase. And so that's something that we will look at in chapter 4. The entire chapter is devoted just to the charging and discharging phase. Yes. 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 That is correct. Yes. The question being asked is what if the current is being constant, especially after it reaches steady state, meaning it reaches full charge, then there is no change in the input current. It stays at a constant level, so it just flows through unimpeded through that inductor. And then there's another important point that I want to make after this. Any further questions? So yes, go ahead. Yes. So if the input current is changing, right? Is that okay? That's the important point that I want to make. So DC flat line, meaning constant value. That value could be 1, 2, 3, 4, 5, doesn't really matter what that value is, but it's constant with respect to time. Meaning if you apply 5 amps of current to an inductor, once the inductance reaches 5 amps of current through it, it has reached full charge. 5 amps will continue to flow through the inductor as if it was a short circuit. Now, when current flows through an inductor, magnetic field arises. That magnetic field gives rise to an opposing voltage. That voltage has opposite polarity that opposes any change in the incoming current. So again, I'll break it down. Input current through the inductor, magnetic field arises. That magnetic field gives rise to a voltage. That voltage has opposite polarity to the actual input current. And so it opposes any change in that current. It's not a direct opposition. It does not oppose the current itself, but it opposes any change in the value of that current. Meaning if you initially applied 5 amps and now it changes value to 4 amps, it is going to oppose that change. It will still go to 4 amps, but will oppose that change while it's still transitioning. That opposition is not direct, so it is not resistance. It is termed as reactance, which is the important point I wanted to make because we will look at that in detail in chapter 5. Chapter 5 is about AC analysis. AC voltage or current is constantly changing with respect to time. The value of the input current constantly changes. So when the input current constantly changes, there is constant opposition from the magnetic field of the inductor. So that's a lot to take in. So let's take a pause while you think on that and let me know if you have any questions. Again, for DC, it's constant. Once it reaches full charge, it's a short circuit. But if there's any change in the input current, meaning if it's AC, then there is constant opposition. So the question being asked is, does it oppose after it reaches full charge or does it happen constantly? The answer is it happens constantly. As soon as it changes, that's when it starts opposing. So if you think about it, let's say it's going to a positive level and then a negative level, right? Different level. So if it's going in a positive level, the magnetic field is set up in such a way, polarity of the voltage is opposite to the incoming. But now the polarity of the incoming changes because it's going in a different direction. Even if it doesn't go all the way to negative, it's going in a different direction. So if it goes in a different direction from 5 to 4, let's say, or 5 to 6, it's increasing. Then that change will give rise to a magnetic field that is in opposition. And so that's why it opposes. Okay, any other questions? Okay. And then one final slide is about the equations for power and energy. Again, we are not doing any derivation. Power is simply the product of the voltage and current. You plug in the voltage equation, L di over dt. and you get Li di over dt. And then energy is the rate at which work is done, W. So energy for an inductor is half Li square. There is a small derivation. Again, we don't do it for non-E major classes. For E classes, we have the entire quarter to study. Actually, the entire academic year to study the circuit analysis. And so we do derivations over there. But again, W is simply half Li square. Okay, half Li square. And of course, these equations are not something that I would expect students to memorize. You can look it up in an equation sheet. You can refer to your notes. It's open book, open notes. You do not have to memorize, but you do have to understand and apply these equations. Okay. So let's move on to the capacitor. Capacitors are nothing but two conducting parallel plates separated by an insulating material. Okay. It's two conductors. And conductors, I mean, they are able to conduct electricity. They are separated by an insulating material. You could take the two palms of your hands together and separate it by air. Air is an insulator. If you measure the capacitance between two palms, if it was possible to measure such a low capacitance, you would be able to get a certain value. Okay. So again, any conductors separated by an insulator is a capacitor. Capacitor stores charge in an electric field or electrostatic field. Similar to an inductor, we have voltage and current equations. They are completely similar in structure, except the V and I are flipped. Okay, we'll look at the equations later on, but let's look at the symbol for the capacitor and how it would actually function. The symbol for a capacitor is simply two parallel lines of the same length. Sometimes one of the lines is a concave shape, as shown here. Sometimes it may have an arrow through it. An arrow, by the way, simply means that the component has a value that is variable. And this arrow applies to all three components, whether it's a resistor, inductor, or capacitor. Okay. Again, if it has an arrow through the symbol, the arrow simply means that the value is variable. It can be changed. So let's take a look at a brief description of what is going on in a capacitor. I'll go over the physics of it a little bit, but after that point, I will tell you to leave the physics on the side and just think in terms of electric circuit analysis. Okay. Trying to reconcile both just leads to confusion. So when I was first starting out as a student more than 30 years ago, it took me quite a while to actually keep the physics on the side, just understand the circuit analysis, and then reconcile the two when you go to a higher level of learning. Okay. So let's say you have a capacitor, right? Two parallel plates separated by an insulating material, right? There is no direct connection between the two plates. Does not have any charge across it, so 0 volts. So if you measure the voltage across that capacitor is 0 volts, you connect it to a voltage source Vs. The switch is open. At some point in time, you're going to flip the switch closed. When the switch is closed, the battery or the voltage source is directly connected to that capacitor. The voltage source has polarity, plus up top, minus at the bottom. There is a charge imbalance. The voltage Vs is at a high level. Vc is completely 0. Because there is a charge imbalance, the electrons in the wire and the and the plate of the capacitor, the upper plate of the capacitor, get attracted to the positive charge of that voltage source. Opposites attract. That's where it comes from. The negative electrons are attracted to the positive terminal of that voltage source. The electrons start moving away from that plate When an electron moves out of its spot, it leaves behind an empty spot. I've stated this before. In semiconductor device physics, that literally is known as a hole. Electrons and holes. Electrons have negative charge. When they move out of its spot, it leaves behind an empty space that is known as a hole. A hole has positive charge. Absence of a negative charge results in a net gain of one positive charge. Hence, you see the plus at the top plate of the capacitor. Okay, and it's moving towards the positive terminal of the battery, so it's moving in a counterclockwise direction. The same but opposite effect occurs at the negative end of the battery, where the electrons are repelled. Opposite charges attract, light charges repel. So the negative terminal of the battery drives the electrons towards the bottom plate. So negative charge is built up on the bottom plate. Positive charges build up at the top plate, negative charges in the bottom plate, they cannot cross over. If you measure the voltage across the two, now you get a voltage that is known as the capacitor voltage, VC. VC. At some point, the charges start building up and VC rises to the level of VS. The point in time where VC and VS are equal, meaning the voltage across the capacitor reaches the exact same level as VS, the capacitor stops charging. Okay, when energy flows into inductor and capacitor, we say they are being charged. When the energy flows out, we say they are being discharged. So VC reaches the full charge value of VS, the applied voltage source. Electrons stop flowing through that circuit. This is an important point that I'll come back to later. So electrons stop flowing through the circuit. When electrons flow in a circuit, what do we say about the current? If electrons are flowing counterclockwise, current I flows clockwise. If you look at the direction of the current, for the source, it's going from minus to plus. For a capacitor, is going from plus to minus, which makes sense because capacitor is a passive component. It follows the passive sign convention. Current should always flow from plus to minus. When it reaches full charge, electrons stop flowing to the circuit. Current I goes to 0. So let's take a pause. Think on that. Let me know if you have any questions. Any questions? Yes. That is, so I will go over that. Yeah. So it is steady state. The question being asked was about, is it any different than steady state? The answer is it's not. Once it reaches full charge, it is steady state. And at steady state, it behaves like an open circuit. But I want to make one important point before I get there. So now I stated, right, the two plates of the capacitor are separated by an insulating material. They don't cross over. So this is the point where I tell you, leave the physics on the side and just think in terms of circuit analysis. Electrons are not flowing through the capacitor. Yet we do state that the current is flowing through the capacitor. Okay. When you first start out, it's hard to reconcile the two. See, electrons are constantly moving, right? So if electrons are moving, with the exception of those two tiny plates, current is flowing through the circuit. Yes? So we state current flows through the capacitor. but physically there is nothing actually flowing through the capacitor itself. Current is flowing through the circuit, so we say current flows to the capacitor. So refer to the capacitor for the purposes of circuit analysis, refer to the capacitor current, similar to what you would do for a resistor current and an inductor current, that it is flowing through the capacitor. Okay. Don't think too much in terms of the physics, not for now at least. Yes. They do. They do. Yes. So that I will explain that on the next slide. Yeah. But the important point I wanted to make was when you apply, and this is again for, whether it's DC or AC, the behavior is the same. But when it's DC, the incoming voltage does not change. It remains constant, right? We have voltage source Vs that has a fixed value. So at certain point in time, Vc will equal Vs. When that happens, electrons stop flowing in the circuit because there's no more charge imbalance. Vc equals Vs, it behaves like an open circuit. Mathematically, we look at the equations next class, but I'll point this out right now. Capacitor current I is C dV over dt if it reaches constant. I'm talking about the concept, not the equation. Concept, right? You apply a voltage, charge imbalance, capacitor starts charging, electrons are flowing in the circuit. At some point, it reaches full charge, Vc equals Vs, electrons stop flowing, current I goes to 0. When it goes to 0, capacitor behaves like an open circuit. So for DC voltage and current, inductors behave like a short circuit, capacitors behave like an open circuit. This is only after it reaches full charge. Exactly, that's going to be the next point. For an AC circuit, it's constantly changing. So when it changes, the electrons start moving again, constantly, right? So if it's, let's say it's DC, it reaches a full charge, electrons stop flowing, behaves like an open circuit. Now you change it. If you change the input voltage, electrons will start moving again. Whether it goes higher, whether it goes lower, doesn't matter. For both cases, any kind of change that occurs in the input voltage, capacitor, electrons will start moving again, the voltage will change across the capacitor. So if it's 5 volts and you change it to like 6 volts, capacitor electrons will start moving again, capacitor voltage goes to 6 volts again. If from 5 it goes back down to 4, again, electrons will start flowing, current will be flowing to the capacitor, again, it'll go down to 4 volts. When it stops changing is when it behaves like an open circuit. If it's constantly changing, then constant current is always flowing through the circuit. This is going to be an important point again when we get to AC analysis. Any questions? There's one more slide I want to cover for the homework, but any other questions? At the end of this chapter, there is a summary slide of all the equations. You can compare all the equations side by side. There is one slide I want to cover. There's not much to the side. If you have series and parallel connections of inductors and capacitors, you can reduce them similar to how you reduce resistors. Inductors add up the same way as resistors, capacitors the opposite of resistors, meaning if you have inductors connected in series, you simply add them up. In parallel, you add up the reciprocals. Capacitors, if they're connected in parallel, simply add them up, C1 plus C2 plus C3, and so on and so forth. And if they're connected in series, then you have to take the reciprocals. Okay. The slide, the summary slide on the next page lists all the equations that you would need to solve. Again, we will look at the problems and the capacitor equations on Wednesday, but do not wait to get started on the homework. Okay. You can answer most of the conceptual questions based on the 2 lectures. All right, I will see you all on Wednesday. If you have any questions, I'll be in my office later this afternoon.